a second derivative test. So in multivariable calculus, you'll see d. I'm guessing that's the determinant, but they have it as fxx fyy minus fxy squared. And keep in mind that this is taking second derivatives of this f function. So we have a function and we are differentiating twice. And then we have this interesting property. If d is greater than 0 and fxx is greater than 0, then we have a local minimum. If d is greater than 0 with fxx less than 0, we have a local max. I don't know exactly why these are true, but I guess it is. If d is less than 0, this is not a local extreme point. So the reason why I say that this is a determinant is because it could be a matrix. Let's go back on that. So we could say D is a 2 by 2 matrix. So D is equal to fxx, fxy, fyx, fyy, which gives us this fxx, fyy minus, and because it doesn't matter how you differentiate, the order doesn't really matter. If you fxy is equal to fyx basically. So these are just taking the derivative of f with respect to x twice, or y twice, or x and then y, or y then x. Doesn't matter. They're both the same for this one anyway. So this is when we have, f of x, y. We're going to have this sort of determinant. If we have, say, f of x, y, z, our determinant becomes slightly more complicated. Now it's going to be a 3 by 3 matrix. So it's going to go fxx, fyy, fzz. This is going to be xy and xz, fyx, fyz, zx, and zy. And to compute this, we have to basically decompose this into 3 2 by 2 matrices. So you can do the cover-up method. You can do it multiple ways. Basically, you take this element and then you cover up here, here, and this is going to be your 2 by 2 matrix. You can also take this element, you can also take this element and then cover up this way. I think it's been a minute since I've done it that way. Let me double check. Okay, I remember. So what you're going to do if you want this element, well, you don't want that element, but you use that element and you cross all of these out and you're left with this to be your matrix. But I'll explain that when I get to linear algebra. So we're going to do the standard. So we're going to go this, cross those out, and then go here, and then cross those out. Well, not those, but we're going to do this step by step. So, okay, so decompose this. So we have fxx. So we're going to use this term, and then we're going to cross off. So we're going to go fyy, fyz, fzy, fzz. Oh, okay, hold on. All right, and then with no knowledge of linear algebra, I'm just going to say now that we're going to have a -1 here. So we're going to minus, and then it's going to be this term. And the reason why we have this outside is because we're going to be multiplying this term by the determinant of this matrix. So we're going to have, now we're doing the second term, fxy, and then do this cover-up method. fyx, fyz, fzx, fzz. And now when we do the last term, I had to redo this stuff because I couldn't figure out how to erase it like I did last time. So now we're going to have this term, fxz, and I get another 2 by 2 matrix. Now we cross these out, and we can leave that like that. fyx, fyy, fzx, fzy, and then you can take the determinant of each one, and then you're going to get this times this product. Let's call it A, and then we'll call that one B, minus fxy times c minus d plus fxz times, let's say, e minus f. I'm not going to write out all those products, but it would be something like that, and you're going to get some number that you can then go into here and be like, okay, well, is it a local minimum, local max, local extreme? But I think for 3 dimensions, this becomes a lot more complicated, and it's not as, I shouldn't say 3 dimensions, I should say 3 variables. This is already 3 dimensions as a 2 variable function. A 3 variable function I guess would be like a maybe 4D, so a 4-dimensional object. But yeah, I have an example, but it's not going to be a 3-dimensional one. It's going to be a 2-dimensional one, so it's going to be a little bit easier. So let's get into it. So let's examine this function. X cubed minus 3x plus y cubed minus 3y. Fx is equal to 3x squared minus 3. Fxx is equal to 6x. Let's look at the Fy. Fy is equal to 3y squared minus 3. Fyy is equal to 6y. What about fxy? If we do fxy, we can see that there is no y term, so fxy is going to be equal to 0. Fyx, similarly, there's no x term here, so it's also 0. So when we take our d, we're going to have a non-negative term, I guess, depending on what points we use. So I'm going to be doing 4 points. Let's say we do the point 1, 1. Well, I guess 1, 1 and f of 1, I guess, would be the right way to put it, but I just have 1, 1, so -1, or my mistake, not 1, 1, but f of 1, 1, like that. -1, 1, 1, -1. Let's make that a different color, actually. And then -1, -1. The only reason I'm including this last term is because this is going to have its own point. So, for example, we can compute what these f of 1, 1 and all of that is. Let's do that real quick, actually. 1 cubed minus 3 plus 1 cubed minus 3, so 1 minus 3 is minus 2. Well, okay. 1 plus 1 is 2, minus 6, minus 4. If we do -1, 1, then these terms are just going to cancel. We're going to get 0. So when they're opposite, we get 0. And when we have them at the same, they're going to be kind of adding into each other. So f of -1, -1. So -1 cubed minus 3 times -1 plus -1 cubed minus 3 times -1 is going to be the opposite of 1, 1. So this is just going to be 4. So these are going to be our 4 points that we're going to be looking at. I didn't really need to do these, but well, I didn't need to find their values, the function values, but I did just for fun. So when we do our second derivative test, remember d is equal to fxx fyy minus fxy quantity squared. So we have 6x times 6y minus 0, or 36xy. So if we do d of 1, 1, this gives us 36, and that is a local minimum, as we can see from this function value. If we do d of -1, 1, we get -36. That would, in this case, this is a saddle point, and this is -1, 1 right here. This is a 0. If we do d of 1, -1, it's again -36. That would be a saddle point. And d of -1, -1 is obviously -36. Sorry, it's late and I misread. This is +36, and this is now a local maximum. As we can see that this is a positive value, and it's a positive forward, and it's the largest of all these values. So if we were to graph something like this, and I know that it's not gonna, this is a very simplified value, a simplified thing, but simplified graph. But if we were to do something, we would have a 2 points where it's like a saddle point. It's so it could look something like that. So we have our minimum and our maximum, and then our saddle points are right there. Doesn't really give us much info. It could be a turning point. All right, that's about it. Thanks for watching.